Hi guys, this lesson is on 4.9 Trig Identities. It's this really new area of math that we've never looked at before called proofs. But as you get into university, proofs become more and more important. They're really what your entire class will focus on if you take higher level mathematics. It's also our last trig lesson, so I'm sure some of you out there are celebrating. So first of all, let's look at the formula sheet. There was this whole trigonometry side of the formula sheet, and it's quite big. We have looked at the first few, so we know that tan is sine over cos. We know the reciprocal trig functions or the companion trig functions, but we're looking today at, if you can see where my cursor is, we're looking at the Pythagorean identity and some other identities. So what an identity is something that we know to be 100% true. It's been proven that, for example, sine squared plus cos squared is always going to be equal to 1. And that comes from the Pythagorean theorem. Now, there's a whole bunch down here, if you look at them. And due to COVID, all of these are going to be skipped. Okay, so this whole row here of all of these what we call double angle identities with two thetas, or sum and difference where they're minusing or adding, we're not doing any of those. However, you can use the same skills that I'm teaching you today to work with all of those identities as well. So let's take a look at what a proof can be. So there's three ways you can prove something. Graphically, so entering a y1, a y2 in your calculator, and if they're the same graph, if they overlap, then you know that they're an identity, they're true. Now, graphically is not something we focus on. It's more of a double checking strategy. It's not going to be a proof by any means algebraically. And that's what we're always going to be asking is algebraic proofs. So graphically is just a double check if you're not sure. Numerically, we'll do a couple examples of numerically. This is where you actually sub an angle in. So I might say, prove this identity for 60 degrees. You would actually put 60 degrees in for theta or for x, and you would make sure that the numbers end up being the same. Now, the problem with numerically is that it only works for that one number. So in my example, it would only work for 60 degrees. It doesn't prove that equation for all angles, which is what we're really after. So what we have to do more often is an algebraic proof where we simplify using the identities on the formula sheet. And I'm going to show you a 2-column proof or a T proof, and you'll see why. But basically, this is something that you really need to get used to. It's very different than algebra. Algebra, for example, like this, we would move things from one side of the equation to the other. So like I just moved the 1 to the other side of the equation. That's algebra. Proofs, we never move stuff in a proof. So I'm going to show you an easy way to prevent yourself from doing that. We've really been training you for years to do algebra because all of those algebraic skills are needed in proofs, but proofs are a very different form of mathematics. You're using algebra within the proof, but you're never moving things from one side of the equation to the other. Now, most problems can be solved by changing to sine and cosine. So if I give you a bunch of, secants and tangents and things, a good first attempt is to change things to sines and cosines. Now, the reason why proofs can be so frustrating sometimes is because there is no one way to solve things. So I can't give you the magic answer of what you can do for every single question and it will always work. Proofs are kind of this culmination of 13 years of mathematics training that we've been giving you, and you have to put all of that together, use all of the skills that you've learned to try and figure out how you can make something look like the other side of the equation. So there's a few tricks that I'll teach you, but there's never just kind of one solution fits all. So sometimes you have to try something, and if it becomes a total mess and gets super, super complicated, you just erase it and try the proof again. That's just the way that proofs go. Now, this has shown up here, and what this stands for is left side equals right side. That's ultimately what we're trying to show in a proof. If our left side equals 5, if we can show that the right side equals 5, then we've proven it. Okay, so that's what we're after. And let's do an example. Actually, let's take a look at some things that are common misconceptions first. Sine squared and sine x squared. These are two very different things that students get confused. And you'll notice that it's really a slight difference. It's just whether the squared is between sine and x right here, or whether it's after the x. And just by putting in brackets, this will clear this up for you. So if I have the squared on the x, that means that the x, which is in the angle position, is the thing that's being squared. So that'd be like writing this. If the squared is on sine, that means that the whole sine x function is being squared. Which, if we think back to what squaring means, it means repeated multiplication. So it means you actually have two copies of sine x, like that. Whereas in the first one, you had two angles of x, but not two sine x's. Very different things here. Now, pause the video so you can write down these helpful understandings. Some of them are off the formula sheet, and some of them I have just adjusted to be the squared version. So for example, the first one here, tan x equals sine x over cos x. That's on the formula sheet. You can put squareds on everything and have the same thing. This isn't on the formula sheet, but we assume that you can figure that out. If I just square everything, it's still the same thing. Here's your secant ratio on the formula sheet. Here's the squared version. Same thing for cosecant. Cotangent has a couple different options. We can think of cotangent as cos over sine, or we can think of it as 1 over tan, both of which you can square and have those identities to work with as well. All right, so here's the first example. We're going to solve these, or prove them rather, numerically. So remember, this is when you just sub in a number. However, I'd like you to make note that this only proves for that number, not for all numbers. Okay, so it only proves for, in part A, 30 degrees. It doesn't say that this identity is going to hold true for all values of theta, which is what we want to prove when we say algebraically. So numerically is just going to show that this works for 30 degrees. So let me show you how to set up a T proof, or a two-column proof. You're going to find your question, which is this. Okay, sine theta times cotan theta equals cos theta. And then they're telling you in the next part theta is 30 degrees. That's what we're going to sub in. You're going to basically underline what the question is, and then you're going to make it look like a T by putting a line through the equal sign. The reason why I like this is because the line represents the equal sign, but you can never cross the line. Write that down. Never cross the line. This is really hard for students to kind of learn for the first time because you're so used to algebra where you do cross the equal sign. You do minus something from both sides so that it ends up on the other side. We've been doing that for years, but now we've got proofs and we cannot cross the equal sign. So all we can do is we can evaluate what we have on each side of the T proof, the two-column proof. So let me sub my theta in. So everywhere I see theta, I'm going to write 30 degrees. And then on this side, I have cosine, 30 degrees. Now, this is really going to help some students. If you ever feel yourself wanting to do algebra, so move things from one side to the other, I want you to simply come over and put a sticky note, a blank piece of paper, a book, something on one side of the T proof. Okay, completely cover it up. That side does not even matter. All I can do is simplify the other side right now. So I chose to simplify this side because I can do this with the unit circle. Sine 30, that's on my unit circle. I'm looking at it in my classroom right now. That's the value 1/2. We're multiplying by cotangent 30. If you look at the last slide or your formula sheet, cotangent is either 1 over tan, which doesn't really help me because my unit circle's only in sine and cos, or cos over sine. So I'm going to figure out what's cos 30. It's root 3 over 2 over sine 30, 1 over 2. So here we go. We can do a whole bunch of different algebra, or pardon me, evaluating here. But basically what we have is we have a 1/2 kind of on the top over here. We have a 1/2 on the bottom, so they can cancel. There's a longer way that I'm going to show you. We've got 1/2 out front multiplied by root 3 over 2 divided by 1/2. Now I'm going to change that divided by 1/2 to be times the reciprocal. Lots of people on the last Google form forgot that you could do this. Okay, this is how you simplify things from the unit circle. Now, we can end up canceling some things here, like a 2 on top, a 2 on bottom. And then on top, all I have is root 3. And on the bottom, I have a 2. I've pretty much simplified the left side of this equation as much as I possibly can. There's nothing else for me to do. I could maybe put this in my calculator and say that it's a decimal, but it's totally fine the way it is. Let me move my sticky note and let me work on, actually, let me move my sticky note over here. I don't want to touch that side. I'm done with that side. You work with one side at a time. Now I'm going to look at cos 30. Look at your unit circle. What's cos 30? It's root 3 over 2. So you're not writing, like, I'm going to erase this, but you're not writing equal signs or anything here. You're doing a proof. So whatever is written below is equal to the step above. Okay, and you have to make sure that's true. When I look through your work, every single row should be equal to the row above. Now, look at what we have. Oh dear, that's not what I want to move. Look at what we have on the left side and the right side. It's the same. What you want to do is you want to end your proof by saying left side equals right side. That's a good way to end a proof. You have proven that for 30 degrees, sine theta times cotan theta is always going to be cos theta. The other way that you can end a proof that I saw a lot in university was kind of this sideways hashtag. They use that as a formal ending to proofs as well. What the diploma usually prefers is the left side equals right side, but it really doesn't matter how you end a proof. Just you have to say something. Let's try again, this time with radians. So we've got to set up our t. So underline the question and draw your t through the equal sign. Tan squared x equals secant squared x minus 1. So the first step when you're doing it numerically is just to sub the number in. So tan squared of pi by 7 and secant squared of pi by 7 minus 1. Okay, this one we're just going to do with decimals. Okay, so what I want you to do is I want you to think about how you would put the left side of the equation in your calculator. Pretend like that has disappeared. Tan squared pi by 7. So you want to square the whole tan pi by 7, not just the angle. So what I'm going to put in my calculator opens the bracket for me. Here's tan pi by 7. I need to square this entire thing. So you do have to have this double bracket scenario going on, or just do tan pi by 7, get an answer, and then square that answer. Okay, what I'm getting for a decimal is this. 0.2319 blah, blah, blah. Now I'm going to do the other side, but the problem with the other side is I don't have secant on my calculator, and nobody's going to have secant on their calculator. Some of the TI Inspires do, but we actually shut that function off when you take the diploma. So the TI Inspires can do a little bit too much thinking for you, where we're trying to test whether you can use your formula sheet and you understand what secant is equal to. So yeah, we shut that function off. So if you have a TI Inspire and you have secant as one of your buttons, don't use it. Pretend like it's not there, because in the diploma it wouldn't have been there. So what can we change secant to? Secant is the companion ratio to cosine. I could look at my formula sheet, find secant on here. There it is. It's 1 over cos. And I could write it as 1 over cos squared of pi by 7. So that's what I'm going to put in my calculator. But let's just be clear. We're going to have to put cos pi by 7, big brackets around it, and square that whole thing. That's what the squared in the middle means. And then you're going to minus 1. So go ahead and pop this in your calculator. I'm going to do it myself. So I got cos pi by 7. I'm going to square it. And then I'm going to minus 1. And I'm getting same answer. So this was 1.2319. And then when I minused 1 from it, let me just pull my t-chart down here. I got 0.2319. So we can see now left side equals right side. So our proof for pi by 7 at least is done. Now let's try algebraically, and this is really the big shebang. This is what we've been working 13 years to be able to do, is an algebraic proof that takes into account all the mathematics we've learned up until this point. So all you can do in algebraic proofs is you can make any substitutions that make sense, and you're really replacing from the formula sheet. Okay, if it's on the formula sheet, you can make the substitution. The first slide we talked about going to sines and cosines, usually being a good strategy for most proofs, not all, but most. And that's actually what we're going to do for this first one. Set up my t-proof by underlining my question and drawing a line through the equal sign. Now the comma is where the question ends. Why are they saying tan x cannot equal 0? Well, look where it is on the left side. It's in the denominator. Can denominators be 0 in math? No. So this is just a restriction, but this has no bearing on how you do the question. You can pretend like it's not even there. It's not part of what you're proving. It's just a restriction. It's just basically saying that we can't divide by 0 in math. So here I go. My right side is pretty easy. My right side is cosine x. Doesn't get much simpler than that. I need to make my left side look like that. So I've got sine x divided by, now I'm trying to make everything sine and cosine. So go to your formula sheet and figure out how you can make tan into sine and cosine. Here it is right here. It's sine divided by cos. So in the bottom there, I'm going to make tan, and I'll color code this so that you can kind of see it better. I'm going to make it sine divided by cosine. Some people get lazy and they don't put the x. There always needs to be something in the angle position, or you're really not talking about the mathematics properly. There has to be an x or a theta or whatever kind of variable, but there needs to be something. You cannot just write sine cos. That's just kind of getting lazy. And I know sometimes proofs are really long and it's easy to do that, but try not to. Now, how do you divide a fraction within a fraction? We've done this multiple times. You write it horizontally. Top we have sine x, and we're dividing by sine x over cos x. Division of a fraction is multiplication of the reciprocal, so flip it. You can put the secret denominator of 1 under sine if you'd like to see the denominator there. And now when you're multiplying, you can cancel things that are the same on top and bottom. So on the top I have cos x. On the bottom I have 1, which we wouldn't usually write. And you can see that I now have left side and right side equal to the same thing. So I conclude my proof by saying left side equals right side. And I just like the sideways hashtag thingy. So usually one side is a lot less work than the other side. Like our cosine side on the right, there was nothing to do there, but there was a lot to do on the left. That's totally fine. But you're looking to keep going until you have both sides the same. And I never moved anything across that line. That line was like no man's land. You cannot move things across that line. Okay, let's try the next one. Set up my proof by underlining, drawing my t through the equal sign. And I'm going to make a suggestion for this one. Do you see how there is, most of it's cos and sine, which is what we want to do, but there's a denominator of cos. If there's a denominator like that, my hint for something to try is doing a common denominator. Like I said before, proofs are not one size fits all. This isn't going to work for everything that has a denominator. The last question had a denominator of tan, but I didn't do a common denominator because it wasn't adding or subtracting anything else. There was no need to. So here, if I've got a denominator on my first 1 over cos x, and I don't have the same denominator and I'm subtracting the next thing, you can try a common denominator. So let's try it and see where we get. We've got 1 over cos x minus. This currently has a denominator of 1. So what do I need to multiply this by to make cos x in the bottom? Well, if I multiply the bottom by cos x, I have to multiply the top by cos x. If you take the original cos and multiply it by another, you get cos squared x. Make sure you're writing that squared in the right spot. If you write it after the x and you didn't put that entire thing in brackets, you're wrong. Now, what did we do with common denominators back in grade, 7 when we did fractions? Well, we can write one denominator and we can add or subtract the tops. Now, you've got to practice identities a lot because you've got to have feelings. So when I look at the top of that fraction, I have a pretty strong feeling that that is on the formula sheet. And it's not on the formula sheet immediately. Like I can't look here and find that exact thing, but I can find this identity right here that has a 1, it has a cos squared, and I could rearrange it so it's 1 minus cos squared. So that's what you got to look for. It's not going to be an immediate substitution most times. You're going to have to maybe do some rearranging. So this is what we're using. That one's called the Pythagorean identity because it's like a squared plus b squared equals c squared, but on the unit circle where the sides of your triangle are sine and cos and the hypotenuse is 1. So this is what it looks like. I think they use thetas, it doesn't matter. And what I want it to look like is this. Okay, because I want to be able to sub it out for something simpler that doesn't have a subtraction. So I'm going to minus cos squared from both sides like this. It cancels on this side. Now this is algebra. This I'm allowed to do. I'm just rearranging it. It's outside of my t proof. I've got sine squared left on this side, and I've got 1 minus cos squared on this side. This is exactly what's in my proof right now, so I can swap it out for sine squared, a little bit simpler. So that's what I'm going to do in this next step. I'm going to replace the top of my fraction with something that it's equal to. Sine squared x over cos x. I would say that's pretty simple. There's no adding and subtracting. There aren't multiple fractions. It's one fraction with a couple of signs in the top and a cos in the bottom. I'm going to stop there because that's about as simple as I can think of this getting. And I'm going to go to the next side. So put your sticky note over this side so you don't try and do anything weird and cross the line. And let's try and simplify sine x times tan x. What should I replace tan with if I want everything in sines and cosines? You look at your formula sheet, you see tan x is equal to sine x over cos x. This is multiplying fractions. There's a secret one here. Top times top. Sine x times itself is sine squared. 1 times cos on the bottom. And that's all I have to do on that side because now left side equals right side. Say that always and end your proof. So we'd never used any numbers in here. We only used variables for the degrees. We didn't sub in 30 degrees or anything. So we have just proven that this is true for every value of x. Now, if cosine from the beginning was equal to 0, that'd be bad because it'd be in the denominator. So we wouldn't want cos x to be equal to 0 because it was in the denominator. But other than the restriction, every other value should work in this equation. We've proven that to be true, except for the values that would make a 0 in the denominator. Let's keep going with more examples. This one, we've got secants and cosecants. And the key with this one is, again, you have to have feelings. So when you look at that and you look at your formula sheet, and as we're learning this, I'm going to point you in the right direction. You need to see what we can sub out for secants, cosecants, things like that. I'm going to point you in this direction first. 1 plus tan squared equals secant squared. Why am I pointing you in that direction? Because if I were to move the 1 over, so let's go back to our notes. If I were to minus the 1 from both sides, I get tan squared equals to secant squared minus 1. Look at the question. Why did I do that? Well, secant squared minus 1 is right there in the denominator. Perhaps if I sub it out for tan squared, I can get this a little bit simpler. So I'm going to go secant squared over tan squared. And remember, I was just subbing this guy out for what it's equal to from the formula sheet. And remember, that wasn't directly from the formula sheet. I had to manipulate it with algebra. That's fine, because I'm not doing algebra within my proof. I'm doing it on my formula sheet. Now, secant and tan, I'm going to just change the tan here. I'm going to leave the secant. And lots of people ask, well, how do you know to do that? I don't. I just keep trying things that I think might lead to a simpler solution. Now, this is dividing by tan squared. Tan, remember, is sine over cos. And then I look at this and I think, well, maybe it would be nicer if the secant was also written with sine and cos. So secant, remember, is 1 over cos. I'm going to change my division to multiplication and flip the second fraction. Every single row that I've written is equal to the one above. That's very important. I can now cancel my cos squareds because top and bottom, and I get 1 over sine squared x. That's pretty simple. I could maybe do one more thing, but I ran out of room, so I'm just going to do it on the other side. That's perfectly fine. What is cosecant squared equal to? It's the companion to sine, so it's 1 over sine squared. Left side equals right side. Proof over. Example D, I'm going to give you a hint for this one because we actually haven't practiced this too much. If we were in regular classes, we would have done this a lot in lesson 4.5 that we actually skipped, but we haven't done this. So your hint for this is to do a GCF. Okay, where am I GCFing? I'm GCFing on the left side of the equal sign, and I'm trying to take out something that's common to both terms there. I've got a sine cubed, and I've got a cos squared sine. They both have sine in them. I'm going to take it out. Just like I might, I don't know, like if I had an x cubed plus 3x, let's leave it at that, x cubed plus 3x, I could GCF out the x and get x squared plus 3. Same idea, but instead of it being an x, now it's going to be a sine x. Same exact thing, okay? It's no different. So what can we do here? We can say I'm dividing out a GCF of sine x. Your GCF always is written in front. And then in the brackets, you're going to write what you get when you divide. So if I take cubed and divide 1 out of them, I'm going to get squared left. If I've got sine x on top and bottom like this, those can cancel, and I get cos squared. Now I've got a pretty strong feeling that that is on my formula sheet. There it is right there. Sine squared plus cos squared is the number 1. So here I go, substituting for this guy, the number 1. And when I multiply 1 by sine x, it's just sine x. I've gotten to a pretty simplified version on the left side. Let's see if I can do it on the right side. I've got 1 over cosecant. Cosecant is the companion to sine. 1 over sine. Let's divide fractions within fractions, but let's do it smart. Let's do it the full way so we don't make a mistake. 1 divided by 1 over sine becomes 1 times the flip, the reciprocal, sine over 1. Bunch of 1's there that don't need to be there. Sine x. Left side equals right side. We are done. All right, we have one more example in this lesson. Here it is. We're setting up our t, and we're going to talk about something that we talked about in Math 10C. We talked about it in Math 20. If you took 30-2, we talked about it there as well. And I'm going to do it in red for a reason, because red usually means bad. How do I tackle this? I am squaring a binomial. Here's what some people do. Again, this is red. Red means bad. Square, square. A squared plus b squared. Bad news bears. That is not the proper way to square a binomial. Why is it wrong? Because what does squaring really mean? Squaring means repeated multiplication. If you write the repeated multiplication, you see that this needs to be FOILed. First, outside, inside, last. If you know that, then math's a blast. And when we FOIL something, we combine like terms, and we get a trinomial. You can see that when I did it the first time the bad way, I missed the middle terms. Okay, that's the actual answer. That's just something that I need you to keep in mind. So this, good math skills. The first way, bad math skills, but also, unfortunately, very common math skills are the red way. So let's do, the reason why I'm telling you this is because of this guy here. The squared is outside of the binomial. So let's write it as repeated multiplication. Okay, let's FOIL it. We can do that. First times first, tan times itself is tan squared. Tan times -1 is minus tan. And again, negative times negative is +1. Let me combine like terms in the middle. There's 2 tan x's, they're negative. And then let me point you in the direction of the formula sheet. This guy here. 1 plus tan squared is secant squared. Let's see if we can find 1 plus tan squared. That's not in the right order, but adding stuff, the order doesn't matter. Is that 1 plus tan squared? Yes. The blue part that I circled, I'm replacing with secant squared from the formula sheet, and I've got the -2 tan that I had to begin with. Believe it or not, that's exactly what we were going for. So this is a good example of where we actually didn't want to go into sine and cosines because it would have made things extremely complicated. If you start getting things cubed and powers of 5 and things get really messy, chances are, that you want to go back and relook at the question. Sometimes if you can make it so that an identity from your formula sheet can be used, it's a way simpler method. It's not always easier to go to sine and cos, but usually that's a good method to try. So here's what we have. Bunch of trig identities to practice on a worksheet that's linked on the website. The answer key is there. I'm just an email away if you need help. And that's our trig unit. We're all done. We have one lesson after this, and then we'll be done for the year. Let me know if you guys need help.